This lecture will be about mathematical description of the model or simulator. I don't know which word you want to use. It is model or simulator. From my point of view, it is almost same. So, the model is macroscopic modeling of the reflectivity, motion and geometry of wind turbines. You already saw it yesterday. Model outcome is not spectrum or spectrogram, but model outcome is received signal, reflected signal. But of course, visualization is based on spectrum and spectrogram, but the output is just signals, IQ data. Why? Because I can make anything with IQ data, but if output will only spectrum, okay, I can visualize, but it is all. But I need raw data. For me, it's like raw data of this one. So it is reason why we do it. What is advantage that you can simulate any output, any input parameter that I already mentioned, and that you can also make like lower or higher resolution. What is resolution? Length of blade element. It is variable. I can change it. Of course, it will be very short. Computation take longer time, but never mind. So it is made advantages. So the presented model was compared with signal with real measurement, not with signal, because if I will compare one signal and simulated signal, it will be different, of course. But we make comparison of spectra and spectrograms. And you will see later that fit very nicely. Of course, lot of differences caused by reflection of environment, of real materials, of real RCS. But the DSC, this component is still visible, flash are still visible, tower is still visible, so fidelity is relatively nice. Model was developed in a MATLAB environment. Of course, it could be rewritten to any other software because it is just script language. So if you want to speed up and make real application, use C, C++, Python, what do you want? Because it is how you will see now, it is just mathematical equations. So why not? You can just convert it. And in present time with ChatGPT or something, it is very easy, just put him and expect in another language, so it is no issue. We focus on single wind turbines modeling. I already told you, not all multiple or wind farms. Why? Because what is wind farm? It is just more wind turbines together. So it is summation of together. So if I will design one, what is difference if I design two and make sum of both signals? It is same. It is superposition. And in case of more wind turbines, we have also problem with fact that will be superposition of influence of both or three. It will be hard to make decision what is influencing which parameter influencing each other. But if I will do it solitarily and works, for second works, okay. If I will see some of wind turbines, it will work also. Of course, the validation is crucial, but it is clear because without validation you have model and you can't be sure if it's true or not. So, reason why we developing model, I already mentioned some of them, so I will maybe some of them skip it. Real radar data containing wind turbines reflection are in the majority of cases not available. But if radar not focus on wind turbine reflections, because we checking areas, there is reflection of everything, every clutter, targets. How you want to separate just wind turbines data? It is not possible because it is superposition of all reflections. But you need to have only measure data of wind turbines and of course surrounded environment because you can't remove it. But imagine if I have wind turbine and there will be blades, I always can measure like this one. So focus only on moving blades. not going like this one where it will be limited reflection from environment. It will be still influence, but not so big, because blade causes our problems, not tower. Tower is static object, it is no problem. So, measurement reflections requires expensive equipment. Yes, it is true. We made it is about total, how I can tell it, in total price of measurement chain was approximately, very approximately 15,000 euros. It is huge money, of course. The majority is for SDRs. Antennas also cost 2,000-3,000 euros, if I remember well. Some amplifiers and so on, wires, but it is not so expensive. But in comparison of price of radar, it is almost nothing, because it is much more expensive. All measurements are really time demanding, because you need big car, you need to load everything, go to position, unload everything. You need power generator, of course, because there is no electricity, and everything connect, then start raining, okay, you everything unconnect and go back to car and so on. So it is time consuming, it is not easy. Also, position of placement of measurement chain is often not available. You will find nice position, and there is no road. Believe me, you don't want all this thing, just get it to your shoulder and go go to some field, because it is very heavy. Antenna with stand, one antenna with stand about 30 kilograms. Computer is easy, okay, SDR is 1 kilo, it is not problem, but this and power generator, it is also not light, so this is little problem. So, and reason for modeling is that we must predict more than extent of verification dataset. So, output of model is not that, okay, our measurement and modeling is the same, it is just validation. But after this validation, I can say, okay, and now I can use for any scenario what I want. And I know that produced results will be good. It is the biggest advantages of this modeling. So, contribution benefits of model. Cover scenarios that is not yet built. It is good one. When imagine that we had somebody came, some wind turbines developer, I want build wind turbine there. And you will just run this simulation and told me, this place not, because influence my radar that is 10 kilometers far away. This place, okay, no problem, it is no influence. Of course, it is not 100% fit, but still you have some image, because you can't know it. You will be guessing if not or not. So this will help you. It will help with new radar location. It is just opposite inverse problem. You have wind turbines and you need to place radar, and you can check it. Okay, it is influence, not influence. Good. And new operational configuration. It is mean new wind turbines with new parameters or new radar parameters. Updating of radars and so on and so. It can cover also widest extent of operational configuration scenarios, different yaw strategies, different PRF, different waveforms, anything. So you can check almost anything with this simulator or this model. It could cover a wide range of environmental scenarios. It is also important because we have digital elevation model. We know light of sight. So I place position of radar and wind turbines to corresponding places in my model like in reality. So I can check it, okay, if will be wind turbine on the hill, radar down, what's happen, or mutual position, also good. It can cover also extremely rare scenarios. What is mean? You have some like bad weather scenario, some really rare big storms, or also something like this. So you can make modeling, you can add validation of this influence of this rare weather, like typhoon, I don't know, something like this. So model generally must be generic and reusable for any parameters. And always your model, you could make more and more extension and add more and more parameters to your model because it's modular. You can add influence of terrain, you can add influence of weather, rain, and so on, fog, and so on, because okay, today morning was really foggy, how it's influenced my radar environment. There is complete structure of our model. Okay, I will stand up because it will be for longer time. There you can see it is affecting parameters. It is input parameters, wind turbine parameters, wind turbine blade parameters, wind turbine blade element, time, what is it? It is PRI, nacelle orientation, initial angle of first blade. It is random variable, but in model you can change it to any time. Then is factors affecting signal attenuation, antenna radiation pattern. Yeah, I can even change antenna radiation pattern, so I can simulate almost any type of antenna. Good. Free space path loss. It is like energy that is lost due to environment reflection. Good. RCS, radar cross section of wind turbine. It is depends of course on wind turbine. Then, so it is like wind turbine and environment thing. Then we have transmitted signal. Clear, because it is, we are on a radar side, transmitting signal. Again, unmodulated pulse, modulated pulse, compressed modulation, coded modulation, what you want. It is just function in MATLAB. Signal okay, transmitted signal, it is go to some. From this parameters also, from these parameters is computed Doppler frequency shift for reflection of the wind turbine for each blade element. Also from this wind turbine parameters is computed evolution of range, because if you have radar and blade, you know the rotation, the length will be changed, like range, slant range will be changing. So generally, I will compute range of individual blend element, how it's changing in time. From range, I can compute delay. Good, because what is reflected signal? Transmitted signal that is delayed and attenuated. Good. And not due to movement, it will be Doppler shifted. So from all this, I can compute for individual blade element and from tower and from everything, from any part of wind turbine. I will compute these three things. I will compute also signal attenuation. It is based on range, how far I am away, because you see already radar equation. And of course transmitted signal, I already mentioned. And then you will take it, all these things together, and make computation of the sum superposition of all reflected signals. Because imagine you have one blade element, and this blade element has own range, own Doppler shift, own attenuation, own delay, but it is delay and range, it is almost the same, it is just pre-computed. And you will compute, so you don't compute one signal, you will compute multiple signals from each reflection, and then if you want total signals, you will just make sum of all signals. Then you make processing of received signals. What is this? It is visualization layer or IQ data or decimating. What do you want? It is just, there is result, this is output, and this is processing. What do you want? If you want make some filtration, something, what do you want? Then you will make saving file and graphical outputs. This could be also this could be also spectrum computation, spectrogram computation, saving file and graphical outputs, just visualization. Model is fully modular, so you can see you could add. There we use only free space path loads. There is no attenuation like polarization. There is no multipath effect. There is not this. You want it? Just put it. Prepare this function and put it. So it is possible make extension more and more, and it will be more and more in details. Of course, it will be computation load will be high and high, but it will be more detailed. So I already explained, and we go to math. So it is simulator input parameters. Every parameter will be described. So what we have there, I will explain you just few of them, just like example, because you will not remember, because of it is half of Greek alphabet, of course, so it will be hard. X, Y, Z, Cartesian coordinates of your wind turbine. X, Y, Z, Cartesian coordinates of your radar. Rotation speed, frequency of rotation speed, delta L, length of element, psi0, phi0, phi0 initial angle, psi0 mutual angle between PRS and rotation of wind turbine, like not blade but nacelle. Yeah. On PRS we have NROT, rotation of radar antenna. This is PRI, it is just a different name, PRI. This is length of pulse, rotation, it is number of rotation, because spectrogram, how many rotation you want to compute. FR, it is rotation frequency, carrier frequency, sampling frequency. Then is calculation of the conditions and revolution. So it is maximal distance, blind distance, elevation, attenuation, and so on and so on and so on. So this is completely same like this, but this is in variables that we are using in our mathematical model. There is calculation of Doppler frequencies, so you can see Doppler frequency depends on rotation, number in each rotation. I have number of wind turbines, number of blades. This is length of blade divided dl. This is number of blades element, and it is a replica because we have 3 blades. So it is really complex metrics. Sometimes we are working with 4D or 5D metrics, because it depends on many variables. And same you will do it for calculation of time evolution. This for computation of ranges between, and again range depends on in which rotation I am, in which turbine, in which blade, and in which blade position. Signal attenuation, you can see we have simplified model. Signal attenuation is just simplified, that is some attenuation, some constant. If you want some more detailed attenuation, just change this function to another that is in more with reality. Transmitted signal, okay, it is easy. We just developed some transmitted signal, and you can see there is TS, and there should be NTS. It is mean it is sampled. Everything showing in continuous time, but it is, of course, it is discrete. Everything is discrete. In MATLAB is everything discrete, so, but it will be more complicated, so it is just remember. Then from range, I will, for each range, I calculate each delay, because range and delay, speed of flight, it is mutual together. And from all this calculation, it is like this. I make computation of the sum, and output will be 3D matrix. First dimension will be n-rot, it is mean first rotation, second rotation, third rotation, and so on, how many number of rotation I am simulating. It is fast time and slow time. It is like this one, and then graphical output, it is same like before. So this picture and this picture are the same, only this is mathematical description of my variables. Of course, you will not remember all of them, but it is not necessary, because you will see later in MATLAB and you can check it. Now, I have quiz for you. What is, because our model is algorithm, of course, it is just algorithm, nothing else. Do you know what is essential properties of the algorithm? It is 4 of them. Maybe you have some base programming techniques, so if you can just guess some of them.
Convergence, rate of convergence, and is
Deterministic with convergence, okay, yes.
deterministic, non-deterministic, is it converging, how fast it is converging, and second thing, there is a region, that the domain of convergence.
Yes. You are quite right. I use little different words, but you are quite right. I have deterministic, finite, resultative, and it is general mass. What does mean? That I can solve entire large group of similar problem for any input parameters. But you say it by little different words, but you say it exactly same. So all these 4 things our algorithm of course fulfill, so we can reproduce this. Now I will describe input parameters. So position, Cartesian, it is night. Blade rotation frequency, RPM, I think that is clear. Length of the blade element, azimuth between gondola axis and PRS, okay. PRS parameter, position of PRS, Cartesian, number of rotation or frequency of rotation, pulse repetition interval, length of pulse, width antenna main lobe, because it is antenna based, it will be wide, it will be narrow, then time of illumination of wind turbine will be different, carrier frequency and sampling frequency, clear probably. Now we go for transmitted signal. How you know, pulse radars can generate, transmit various type of pulse signals. It is just a matter of changing function. And honestly, I think that all of them, majority of them is already programmed. Usually we use own function. Why? Because I have more control on my functions than on like built-in function, because sometimes we use it, they use it some different definition of parameter. It is not mean that it's wrong, but I like control on this, so it is better develop own. It could ranging from classic modulated square waves, unmodulated, or modulated only with sine wave, to more complex signals for pulse compression. Input parameters will be for transmitted signal. Carrier frequency again, sampling frequency, pulse repetition interval or inverse PRF, pulse width and type of modulation or type of compression. Transmitted signal artifacts, it is important thing, because the whole model and simulator is quite computerly demanding. So we always looking also for optimization. If I will use something more times, I will compute only once and then use it, because you don't need to imagine if you want to model like in previous slide, like on this one, for any sample I could always generate not the whole signals but only one sample, and with next cycle another sample and compute it again. Why? I will generate the whole signal in one time and just take it first, second, third, fourth sample and so on and so on. So it is much better, it will be quicker because it not will be under cycle, and usually you do it with matrix operation, because MATLAB is just matrix, it is nothing else. You know what is shortcut of MATLAB? Matrix laboratory. Yeah, exactly. It is just metric, it is nothing else. So, transmitted signal artifact like Rentschler independent on Doppler and long-term amplitude behavior. So, I can develop in one time and then use it. Then, receive signal amplitude. It will be propagation, atmospheric attenuation, free space path loss. Optional can be like attenuation in the atmosphere, polarization losses, clear rain, fog. What do you want? So you can add it to this part. Then receive signal amplitude will be for sure affected also by antenna radiation pattern, because it is depends where is my maxima in radiation pattern, what is which cyclopes there will be, and so on. So our simulator support only monopoles solution, one antenna for transmitting and receiving. We don't work with bistatic because it is very complicated and you don't need it. We don't need it, so it is just simplification of our model. Then also there is radar cross section, so RCS separation to individual components. And now we don't take the whole wind turbines and compute RCS. We divide it to 3 different parts. Tower, nacelle, blades. It is better for us because tower, nacelle, it is not moving. Almost. Nacelle is slowly moving, dependency on wind direction, but it is relatively so slow with PRI that is static. So MTI filtration, it is just static object. But blades, okay, we take care only about blades, it is high speed. Multipath effect you get add, but it is very hard to model and we don't implement it. It is just our simplified model. It is possible to do it, but it will be very, very complicated, and I have personally feeling that contribution of this will be very low. Because with any multipath it is very big attenuation. More multipath, more attenuation. So influence to your model results, there will be some, but not big. Imagine also, where is wind turbine located? In free environment. Okay, there will be some reflection, but not so big one. Definitely, you don't have wind turbines and some skykeeper or something with big reflection surface, if you get my point. So we just decide, no, we don't want to modulate it because we don't need. And it is in receive signal amplitude probably all. Then is range deviation calculation. Range depends on phase and Doppler effect calculated upon range deviation from the reference plane, perpendicular to propagation. So it is like this. Of course, this this elimination of this artifact is caused by limited arithmetics, because in MATLAB you don't have infinite precision. So we use majorly only single precision, because it is much quicker than use it in double precision. But again, if you want, switch it. It is universal. Is it possible? Then range deviation calculation depends on type of wind turbines, dimension of rotor height, discretization of rotor at blade, of course. Because if I have one blade divided to 10 elements or 100, it will be 100 different ranges or 10 ranges. I know that change will be small because it is just elements one by one, but still it will cause it this, how we saw it already, result from simulation, this spreading in spectra, because it is different. Each element has different speed. Elements that are close to nacelle, they have very, very low speed. End of the tip, very, very high speed. It is Doppler, generally. Then is wind turbine Doppler signature. It is computation of the Doppler depends on wind turbine, again blade elements, elements position, and first time PRI. They are there, Doppler effect sampling. It is first parameter of radar. And what is computational principle? Then we first compute speed of each element, or blade, but blade element, of course it is independent. Computation of radial speed of each element with respect to PRS, because we need compute first independently on radar what is speed of each element. And based on this speed, it will changing distance and all other things, of course, with respect to PRS, and computation of Doppler frequencies of individual elements. And from the last element, where will be highest speed, we could evaluate if aliasing occur or not occur, because it is clear. The rest, if for the end of blade not occur, the rest is fine, because it will be lower Doppler shift. Then wind turbine time delay signature. So each blade is again has own time. It is clear. If it has different range, then is different time delay, because range and time, it is connected through speed of flight. So computation of time delays of individual blades. Each blade element has unique time delay and frequency shift. This must be clear. And then you make summation. So, and combination with Doppler shift, this leads to 2D signature in range and Doppler, and it is result that I show you already from simulation. This free sine wave and all these things. So, can I continue? I think yes. Then it's assembly of model output. So the total received signal is in given resolution cell, It is important because it is one resolution cell, one wind turbine. Is then sum over all elements and all turbines. And imagine if you have wind turbines, more wind turbines, then what's happened? You need compute in more resolution cell all the model. And complexity like very quickly growing up. Result of model is reflected signal from wind turbine. I will show you signal structure description. It is in 3D. It is 3D matrix and contains complex IQ data. So important amplitude and phase. It is important. Output are metrics of received signal in each turn. In each turn is different, of course. It is time variable. So we have definite number of rotations. Usually we modulate up to 20, something like this. Why? Why not more? Because it is depends on speed of wind turbines. You definitely won't see this periodicity of end tip of the blades, because when you see periodicity, then it's clear that will be similar. Of course, if you will watch it like 20 minutes and there will be change in wind direction, then amplitude may be little growing up or increasing, decreasing, or changing rotation speed, the periodicity will decrease or increase. It will be like breathing, if you understand me. There will be some changes, but you need to simulate lot of turns to saw it and make definition of these changes, and it is also possible. I will show you later, tomorrow. And imagine, I always told you that radar make detection in individual resolution cell. So I have one row of cells for one resolution, for third one, it is like matrix also. And in one resolution cell is wind turbine, in 5 of them is not wind turbine, in one is, there is, it is almost like sparse matrix. Majority of wind turbine cell will be empty, do you agree? So it is mean I don't need compute in each resolution cell. But where I need to compute? Only where is located of wind turbine. So of course I do it for the whole rotation, but sometimes I saw it, this wind turbine, and in some azimuth I didn't saw it. So generally, where you don't saw it, don't compute. What will be result? 0. So it is not necessary. It is big speed up. You will see later. All samples, so you will compute all samples of signal in one period, and the total metric signals output is this matrix, but be careful, you also need to put all metadata about your simulation. Or save your Excel file what you simulate. It is not important, but the metadata please always save. Because why? Output is signal. From signal you can recognize what you have, which was your setting. It is just output. And when you do it, you will compute spectra or spectrogram. You will see something like this. So in the next slide, I will show you example of output metrics. This IQ data. This is so-called visualization layer. We use it only 2 things, spectrum and spectrogram, because it was for us enough. I don't know if we are missing something, if you have some idea what we could add, what should help us with some analysis. I think that spectrum and spectrogram in this case is enough. But of course you have IQ data. If you want to process with some other visualization, why not? So there is our Doppler shift. There is number of rotations. So you can see I just compute for 6 rotation. This is one sine wave, second, third one. This is flash. You can't do it anything with flash. Flash are flash. This full of spectrum. And this is like for it is individual cuts in individual rotations. It is this one. From spectrum, I don't think that you can see something. Yeah. You can see number of blades. 1, 2, 3. 1, 2. Where is 3? This means that blade. This is tower, and blade is rotating, and blade is just in position parallel with. So you don't see it. And for this 3, so 3 times span 1 rotation, you don't see it. This main lobe. it is clear because always is hidden under tower. I don't know if okay, this second and this is almost this you can see it is always after 120 degree if you will recompute to time, but it is depends on the sampling frequency and all these things. But it normally standard is like this one, all three blades are visible and this is 0. So this main lobe is always same, and these three, they are moving. Unfortunately, it is not like there is not so big periodicity that you can see, because it is like recovering, like it is flowing. I don't have free hands, it will be better, of course you will saw it, but it is something like this. But you will saw it. I have a really nice one MATLAB tutorial where you just press arrow and it will be switching, so you will see this movement in spectra. This is our signal structure description. What do you can see, it is just from workspace. It is 3D complex double, so it is this 3D matrix IQ data. There is, what do you think that is this one? Tower, exactly. 1, 2, 3, and this is phase. There is rotation index, fast time, and phase magnitude and phase. It is like example first, second, third blade. But from this you can't see almost nothing, if you understand me. It is just we just make visualization with Karel of this, but we never use it like this raw simulated output signal data, because you need to saw in spectrum or in the spectrogram. But output 3D metric is file, so it is IQ data, so it is presented amplitude and phase. And spectrum is of course taken that we compute FFT through all rotation, and it is one spectrum. Through other rotation, and again another spectrum, and so on and so on. So n-rot is number of rotation of the radar system. It is like 1, 2, 3, 4, 5 in spectrogram, and rep is number of recurrence periods in the area of interest where wind turbines are located. We call it slow time already. And ns is number of signal samples in one repetition period. It is fast time. So slow time, fast time, number of rotation, 3D matrix. And there is picture from MATLAB. So we go for mathematical model. You already saw it, this one, so I suppose that you remember. And there is like depicturing in 3D Cartesian coordinate system. So imagine there is wind turbine and this is your rotation. And there is nothing in the rest. So we don't compute there. Why? There is nothing. So it is like area of interest, if you can. This developed simulator or model support any number of VTs and one PRS placed in any area, but usually in any area it is true, but for us it is like 0.000, if you get my point. You can place it everywhere, but you always compute delay Doppler shift from this point where is antenna. Okay, I call it that is where is radar located. No, where is like antenna located beam, where is just transmitting this point where is transmitted energy. But I will call it for simplification radar, it is better. So the blue triangle adds the vertical dimension and show the slant range from the radar to the rotating column of the turbine. So we are in azimuth and this is like elevation. And this is results of all computation. Of course, I will show you detailedly how we derive this frequency, but generally it is our model. It is only one equation. It is not looks so complicated, but believe me, it is little complicated to compute this one. So, it is output matrix, ID rotation, first, second, and so on, slow time, which PRI, where I am, in which PRI, fast time, in one PRI, samples. This is constant, and I told you, we use simplification. Everything is attenuated the same. It is just constant for us. What will change if I will put another attenuation? Change of color, if you get my point in the output. So for me, I want to see what? Behavior. So for me, it's not important if it's, how to say, if it will be real value, if it will be reflection 20 dB or 40 dB. I need to see a behavior of the evaluation of this one. So this is just constant. You won't change it to attenuation of real radar to real environment. Yes, so compute in more detail, but again will be constant. You won't compute attenuation for each individual blade element. I think that is nonsense, because it is so small range that will be almost same, but you can. Then not will be constant, but it will be there and it will be changed. And check, there is signal, it is received signal, and received signal depends, it is signals T. So what is ST? It is transmitted signal originally, but received signal bude transmitted signal minus delay, time delay, exactly. But time delay is depends on ID rotation, ID blade, ID element. One wind turbine, 20 rotation, and 3 blades, shifted 120 degree, of course. And each blade has sections, these elements. By the way, there we make one more simplification. You can choose only blade element of one size, and each blade has same number of element. It will be so complicated, this condition, if one blade has, I don't know, 5 elements and second 50. It is not necessary. And honestly, the produced outputs will be weird. It will be odd, because one blade will be simulated with higher resolution than second one. I think that is not necessary. I think that is clear. And what is this? It is Doppler shift computed. And Doppler shift is computed based on, it is Doppler shift. What is, okay, how you will shift signal in frequency, multiplication by complex exponential, AJ2PF Doppler. But F Doppler again based on number of rotation, number of blade, number of element, and TM, what is slow time, which PRI. So I know it is one equation, the whole model, ale pretty complicated. It is not so easy. Why we computing? It is how to say. We develop this exact model is relevant for infinite arithmetic accuracy, implementation by range deviation, reduce number of wavelengths modeled. Why we don't use this wavelength modeling, how we already discussed? Because reflection will have random phase, I already show you. And this random phase of reflection will cause us problem if I will do it by different way. So I don't compute the whole range, but only range deviation, and then we can model small range of deviation around a reference distance, around just blades, and not full absolute range, if you get my point, because it is differences, because this avoids tracking millions of wavelengths and makes the phase numerically stable, because it is just difference. And phase, if I will compute just difference phase between elements, then there will be some small difference. But if I will compute always from PRS, wall signal, reflection of Doppler and back, and so on, then if I will use central frequency 10 GHz, lambda is 3 cm, target is at 30 kilometers, I have approximately 1 million wavelengths that I need to compute. You don't want to do it by this one. So it is clear why we do it from range differences. And in case that I make range deviation instead of absolute range, I can constant phase offset ignore, because it depends only on differences of phases, and it is not for me important. So now we go to slides where is base geometry parameters. So first we will compute this distance. It is to nacelle to rotor. So I know this, I will compute this. So it is x, y, z position of wind turbine minus x, y, z position of radar squared. It is in 3D. One number, because it is this one. So it is okay. Then we compute azimuth with respect to PRS and elevation. So elevation and azimuth. If we know distance, it will be always constant. Elevation, it will be always constant. Azimuth, it will be always constant. No, it is to center. So it will be constant. It is like when we modeling and blade is not present, like this point only. So these three parameters is constant always. So I can compute only one time, not during each modulation. So it is a good example of optimization. So, and which kind of optimization we are doing? So it is visibility and geometry gating. And this we will do it first time before anything else how is written. Why? If in my resolution cell is not wind turbine, just ignore this place. Just don't take. So what we are doing first time? We have metrics where each cell is one resolution cell. And first time I will check where is wind turbines, where is my radar, what is range of my radar, what is blind zoned my radar, and then told check in which cell is wind turbine visible, and ignore everything else. So you can have complex scene, and then you will see that only in three cells is wind turbines. So you will compute only reflected signal in these 3 cells, and everything else is ignored. So imagine you can have it 1000 cell, and you will compute only in 3. And you not need to check in every cell. It's present, no. Yeah, is present, no. Is present, no. In every run. You will check it in matrix one time, and then just, it is classic binary decision. Is present 1, not present 0. And you just pick up coordinates where is 1. It is good simplification, because if you will do it like hard way for each one, it will be complicated. Then It is first thing, okay, where is present, where is not present, but what does mean that is present? Of course that, how to say, wind turbine is not moving, it is still present in some position, but it is present with respect of my radar that is rotating antenna. So, okay, you and you are wind turbines. Present, 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 and nothing. So I can ignore everything. So just in these cases I will, okay, there I need to compute, rest, ignore. Then we make also fast time range optimization. We are working in range bin space. So we don't waveform simulate sample by sample. We just do it in range bin space. Convolution extremely demanding operation. You probably know it from a maths lesson or some signal processing. If you will have longer, how to say, longer length of signal, like transmitted and received, the convolution is always like shift, multiplication, summation, shift, multiplication, summation. It is just classic convolution. Convolution in time is slow. So and what is opposite operation of convolution in frequency domain? We are in Fourier transform. Convolution in time domain is multiplication of spectra in frequency domain. And multiplication of metrics. Yeah. Laplace, the transform, Fourier transform. It is honestly, I always say to my students, all these transforms are so similar. Don't have fear from transform. Everything is linear, time invariant, and always it is just transfer to another space. Okay, we can work in time, we can work in frequency, we can work in S-plane if we have Laplace. If I am in discrete time, I have the transform. But it is still same, it is still same. It is just little different formulas. So, convolution we compute by FFT. You need to select right sampling rate. Not make so big oversampling. It will be much more samples and takes time this computation. And where is possible, make decimation where is appropriate. Slow time optimization. Separable model. So summation of individual contribution. Wind turbine echo is sum of many independent blades elements contribution. So you can easily make vectorization. Don't think that our model works like for cycle, for each blade, for each element. It will be rotation, time, blade, element. Yeah, it will be maybe 5 or 6 for cycle, like inside 4 cycles. You can't compute. We always make vectorization, so everything is like vector multiplied by matrix, matrix by matrix. We compute everything in one time. And MATLAB is really good in matrix operation and very, very quick. Sorry, I just will. CPI length matched to physics. So pick CPI to cover a few blade pass periods. So, but short enough to limit range work. So it is means not take so long period when it's not necessary. Windowing of FFT. Apply slow time window before Doppler FFT to suppress side lobes. If you will do it in frequency domain, you can't do it simple by simple. You will do it in one time, this windowing. And sparse per bin processing, run Doppler only where 5 stamp power is higher than some threshold or where visible masks say VT is possible, wind turbine is there. If it's not, don't compute Doppler where it's not wind turbine. Multi-turbine or farm, superposing turbines but share pre-computed antenna gains, range delays, and so on and so on. Everything what you can compute one time, don't put 2 cycle. and then it's just standard numerical implementation. Try to make as possible vectorization of the algorithm. It is really speed up. Cache of often used results, pre-results. If you use it something, just cache it and use it just from memory. Single double precision. Single precision will be much quicker. And if you don't need double precision, why do it in double precision? And of course CPU, GPU computation. I must say that this is just future. We don't use it. GPU computation until now. In this model, we use it in some other research, but not now, not in this one, because it was not necessary for us. Okay, we will go lunch. Okay, so please check. I will continue and I will do it visibility. Check visibility of wind turbines. So it is classic. What is this? Blind zone. What is this? Ambiguity range. I am outside of my radar. So if will be wind turbine there or wind turbine there, ignore. Just ignore. Don't compute, even if it's present, because it is not related to your radar. So max, I think that I can skip this one because it is maximal distance and minimal distance. We already discussed it and we have tutorial. So what is mathematical condition? It is each range bin. You can okay. It is in each range bin, so you can see a grid and you check it in a range where it's possible or not. You will ignore this, you will ignore this. Orange one, you will ignore area because it is outside of your model. And condition is this: 1, we are in green zone; 0, we are outside of green zone. It is easy. I can't read this one condition, but it is not necessary. I think that principle is more important. In beam visibility, it is interesting because imagine we have this. Okay, first I will show you this one. Do you see this individual range cell? And you can see when you are far, this is longer than there because we are in polar coordinates. And still this one is one range cell. I put this picture to understand what is range cell. And imagine it is position of one turbine, second turbine. There we have like example 1, 2, 3. So we have like position of radar and it is rotation of my antenna. So you know that this white place I can completely ignore. There is no wind turbine, just ignore it. And there is green area. Why I am interested in this area? Because do you see this one? It is main lobe of my antenna. So I am just on the edge of where I see wind turbine. And by scanning speed I do it this one. Now I saw one wind turbine, both wind turbine, and so on and so on and so on. And why end of my coverage is there? Because I am just on edge of the last antenna and everything outside is 0. So I will make computation only in this green area. What is outside I am ignoring because there is nothing. Okay, there will be environment, but I am curious in wind turbine reflection. And this is in 3D. It is similar. I will compute in this, but we ignore all these others. And imagine, so okay, I will. Next one. So theoretical range of azimuth, this green area is defined maximum of this minus minimum of this. Of course, it is this difference. You can see it is just two angles. The rest of surrounded area is ignored because there is no wind turbines, and range of azimuth considering this is this one. What is difference between this one and this one? I don't know if it's clear, but this is like inside and this is with beam width. So in beam visibility, computation depends on range of azimuth considering antenna and also on antenna pattern. It will be so wide, narrow. Of course, it is depends on this. Everything you can choose in our model. So this rotation angle psi, we could compute it 2p divided 2p ri divided t r rotation. It is time of one rotation, what is 60 divided f rotation, and so on, so on. So number of periods in the area of interest where wind turbine is visible is division of these two values. So this means that in beam matrix, visibility depends on range of azimuth, rotation angle of the antenna per second, number of rotation, and antenna RPM and rotation period. Only on this thing. Lunch? Lunch. Okay, please, one more slide. One slide only, and I will finish with in-beam visibility. So, this is matrix of visibility, in-beam visibility. Because visibility, I call it blind area and maximum area, and this is in-beam. It is little confusing, it is two visibilities. So, it is again mathematical condition, and what is this? It is antenna diagram main lobe definition. We just for simplification use it Gaussian shape. So it is Gauss shape of main antenna lobe. If you want another main lobe, just put another main lobe. It is just function. And check this what I want to show you. This is azimuth of PRS, how my antenna scanning area, and in some azimuth of PRS I see first wind turbine. I don't see second and third one due to position. I see one, and what this means this if this number is higher and higher. I see only small part of wind turbine, bigger, and then go to down. Exactly. When you are exactly direction in a nacelle, you will see maximum and then go out. In this case, my detect overlapping wind turbine 1 and 2, but each wind turbine is in different cell. But I will see. So there is area where I see 2. Then I will see only second, and then I will see second and third. And then so I will compute there, and there. Rest you can ignore. So in this case I compute only for one wind turbine, therefore 2, therefore 1, therefore 2, therefore 1. You can see this big simplification, it is really big simplification. Lunch. Yes. But we are in good time today. Okay. Thank you, and we go.